Hello everyone, my name is Abhishek Bansal. In this video, I am going to talk on the window utilization. The window utilization is the word that you would find in the manuals. What is the window utilization factor? When while designing the transformer or doing the manual calculation of the transformer. So the window utilization factor is generally denoted by KU, and this actually means what is basically the amount of copper that is going to appear in the window area. So this window utilization is the same whether I am designing a transformer or I am going to design a good quality of a customized inductor. So when we have to do that, this is valid for both the transformer or an inductor. So the window utilization simply means what is the amount of copper that appears in the window of the transformer. So what is basically a window area, or by the copper I meant, if suppose I am going to draw a window copper area. So this is basically this window. Before I come to this thing, this window utilization factor, it basically governed by 4 factors: S1, S2, S3 and S4. I am going to take all these 4 main factors separately also. Basically this Ku is the product of all these 4, and this S1 is basically a wire insulation, this is the wire lay fill factor, and this is going to be an effective window area. Okay, and this is an insulation required for the multi-layer windings or in between the windings. So if suppose I am going to say this is the copper window area, and then this area would be what? It would be taken by the bobbin, it would be taken by the tube, it is going to be taken by the margin, it is going to be taken by the wrapper insulation, it is going to be taken by the layer insulation, it is going to be taken by even the magnetic wire insulation. So that is going to fill factor. So and this would be our copper area. So the window area that is occupied by the copper, or the amount of copper that appears in the window area, it's a window utilization factor. So we have just seen that this window utilization factor is the product of S1, S2, S3, S4. Now let me take it all these things very separately. Now let us take the factor 1, S1. S1 is basically what I have mentioned, it's basically a wire insulation. Okay, the wire insulation, and the wire insulation, it will mean what? It will means the conductor area, or similarly it will can mean the wire area. Okay, so whether it's a high current transformer or a low current transformer, okay, the ratio of the conductor area to the total wire. So I am talking on the ratio of what? I am talking the ratio of the conductor area upon total wire area. So this ratio I am talking of, I am not taking exactly here now what is the actually the conductor we are going to take, and in a high current transformer I am going to take a low current transformer. I am taking on the basically, I am not talking on the ratio now. So the ratio basically depend, the ratio basically where not, it's not even the constant ratio, it's a variable ratio. It varies from 0.49 0.9412 to 0.673, and obviously this will depend on the wire size. So the thickness, okay, so if we are using a multi strands of the wire, or we rather going to use make a multi strand that is going to consist of fine wires, and that is going to give us, it is going to reduce our skin effect. So it is going to have an effect on the window utilization area Ku. Okay, so what we have seen here is that it is not only dependent on the wire size, it will also depend on the insulation coating also. Okay, and So this was basically our first factor, S1 insulation or the wire insulation or the conductor area or the wire area. Now let's go on and S2, that's the fill factor, or rather we say it's basically what, wire lay fill factor. I am going to write it here. I am going to do S2 fill factor, rather it's the wire lay fill factor. Okay, so this fill factor is basically wound area or a usable window area. So whether you say fill factor or a wire lay, we are going to talk for the usable window area. So when we are going to wind a large number of turns, when I am going to wind a lot of turns, I am going to use it, because you would have seen that okay, in a practical or like in a linear transformer, we can have a number of turns of even 900, 500, 1000. These are very common for a simple small transformer, you will find it. Whereas for a bigger transformer like a distribution transformer, or going to have another kind of transmission transformer, these terms are huge. So these, when we are winding a large number of turns tightly on a smooth surface, so the winding length is going to exceed the calculated value from the wire diameter. Okay, so how much increase it gets? 10 to 5%, 10 to 15% increase we see. Whatever value we are going to do the calculation, the theoretical calculation, what we are going to do it, the calculated value, so the winding length is going to exceed by 10 to 15% of this value that we are going to get it manually or by using calculator, and that is going to depend upon the wire gauge. Okay, so if so like if I am going to use I am using an AWG standard only, American wire gauge standard. So if suppose I am using an American gauge wire, say 10 to 15, or sorry 10 to 25. So we have actually, this is already a fixed table which is already established at 10 to 25 for a wire gauge of 10 to 25. The wire lay factor is 0.9. So this is in highest point 0.9, and the wire lay factor goes from wire decimal. It was 0.9 here, it was 0.89. We will see the wire lay factor go from 0.88, 0.87, 0.86, 0.85. So these are the different three six I have drawn. So these are for the different wire gauges, but here only we see 85, 86, 87, 88, 89, 0.90. Okay, this is for the 10 to 25 wire gauge, this is for the 26 to 30, this is for the 31 to 35 American wire gauge, and this is for the 36 to 38, and this is 39 to 40, and this is the 41 to 44. So these are for the layer wound coils, and we can have a, if we are going to have a, so this if this lay factor is not even constant or same for all the American wire gauges, AWGs, or the gauges, whatever you go, how you are going to pronounce it. So it's basically 0.9 to 0.85. Okay, but this is for a layer wound coil. If I am going to use a random wound coils, here we have six different values. In the random wound coils, we are going to have only 3 values. Like if suppose the 10 to 22, here it was 10 to 25, so it would be 0.9 in that also, in the random wound. Okay, and if I am going to have 23 to 39, the value is basically 0.85, and here we have seen it was basically 26 to 30. So this basically took, this was basically for 26 to 30, 31 to 35, and then 36 to 38. So here we have 3 here and then 39 to 40, but here we have 0.23 to 0.39, 0.23 to 0.39. Okay, so not 0. Sorry, it's a wire gauge of 23 to 39. So it is basically 0.85 here. Okay, and for 44 to 40 to 44 it is a 0.75. So for a random coils, the the wireless factor goes to even 0.75, whereas in the case of a layer bond coils it was only 0.85. So there is a 0.10 difference of 0.10. Okay, so now we can have a different kind of winding arrangements, like the winding arrangements, the square winding. We can have a square winding, we can have an hexagonal winding, and the simplest yeah. Okay, so the one I have already talked on, that the random one coils, the layer factor is going to vary from 0.9 to 0.75, and for the layer one coils is going to 0.90 to 0.85. And but for the, if we are talking on the winding arrangements, the square winding is going to have a theoretical fill factor of 0.785, and I have already said that this is going to be 10 to 15% is exactly winding length is going to exceed the calculated value by 10 to 15%. Okay, so we need to see that this winding, that is basically that we are achieving this. It's not something like that is basically okay, we have just blindly done some calculation. It's basically we are trying to achieve it when we are designing the transformer, or even when we are designing an inductor. So either you do it, employ some engineer or technician, but if we are going to have a let's say we are going to have in a we will want to have a winding pattern of 0.785. So there is also a procedure like how we are going to achieve these winding factors, different fill factors. Okay, and one I have talked on the layer and the random wind coils. The second I have talked on the winding arrangement. Now I can similarly talk on the idle winding on the rectangular bobbin. Okay, the again when we are winding a rectangular bobbin, or even when we are winding a tube, the actual winding height in the region is going to exceed the calculated winding height or build. Okay, and we use the word, or not we, generally it's not used by me, it's given in the manual only, that this is going to exceed because of the bowing of the windings. It's a bowing of the windings. Okay, bowing of the windings, and this amount of bowing on the depends on the proportion of the winding and the height of the winding. So usually the available winding, it should get reduced by 15%. Okay, and we are using a round bobbin, this bowing effect is negligible. So this bowing effect depends on what kind of bobbin we are using. We are using a rectangular bobbin, or we are using a round bobbin or a tube. Okay, so there are basically many techniques like, okay, how we can minimize the bowing effect, how we are going to ensure how we are going to ensure a minimum build for the random or the layer winding or the round bobbin. So basically these things are that, okay, this is basically related only for the manufacturers only, because like what kind of bobbin should be used, whether we should use a round bobbin, rectangular bobbin or a square bobbin, and what's going to give an bowing effect, because like I have seen that in the case of round bobbin this effect is negligible, whereas in the case of a rectangular bobbin the actual winding height is going to exceed it. Moreover, the amount of bowing is basically depending on the proportion of the winding and the height of the winding. So this is basically our second factor, that was the fill factor. The third factor of the window utilization is an effective window. Okay, let's talk on the third factor. Let's talk on the third factor, window, effective window. And the effective window area. So this is basically a effective window only, effective window or an effective window area. Basically this is a usable window area, or we basically say the window area. So what basically we are basically saying that this effective window is going to define how much of the available window space may actually be used for the winding. So that's why it's called an effective window area by name only, and it's again going to depend upon the bobbin configuration or the tube configuration. If we are using a layer winding that uses a tube, it will require a margin, and this margin dimension will again vary with the wire size. So but when we are constructing, there is a standard, industry standard for the layer insulation thickness, which is basically based on the diameter of the wire. Okay, like a layer insulation thickness you might have heard, it depends again upon an AWG standard. So like 10 to 16 AWG has the insulation thickness of 0.01. So these are the industry standards defined. Okay, so a single, if we are going to take a single bobbin design, it offers an effective area between 0.835 to 0.929 for the laminations. Okay, now if I am going to talk on the window utilization for the let's talk on the single bobbin. So if I am taking a single bobbin, so it will have one effective window area, that it is noted by WA, effective window area. Okay, it will depend upon whether it's a lamination we are taking for ferrites. Okay, so the lamination, for lamination it is 0.835 to 0.929, for ferrite it's 0.55 to 0.75. This is a single bobbin. If I am taking a two bobbin configuration, it's going to give us an effective area between 0.687 to 0.873 for the tape C core. Okay, so it's not similar for each and every component. That is basically one of my one of the convincing factor for the non-linear theory. It's basically known everywhere. It was known even in 1800s, 1900s, because these are the calculations from old texts only. Okay, so and this is basically established not by me, by scientists and by the manufacturers and the industry standards. So this is okay. If I am going to use this thing, we are going to get this factor in this, we are going to get this factor in this. So nothing is basically a constant or linear as basically, okay, this is called a science. Okay, it's not a universal here, it varies in each and everything. In the last we have seen at 0.90, 0.89 it was varying. Okay, so it's not a linear, complete linear, it's non-linear. So like similarly, if I am going to move on toroid, we are going to even we are going to have a very different value. Moreover, we are even going to design, we are going to even define, like I am using an, because I can say if it's not a toroid, what was basically an effective window? It was basically how much of the available window we can actually use for the winding. So what we are doing, we have a core, we want to know wind it. So how much actual available of the window space we can use for the winding. So that is what an effective window is. But if I am going to use a toroidal here, if I am going to use a toroid, we can say how much of the available window. Okay, so we need to basically, there are basically many standards there, because okay. Now if I am going, now let me take a little bit of in depth only, little bit of. So this, suppose I say I am drawing a, suppose if I draw suppose a bobbin here. Okay, this I am talking of a single bobbin. So I am taking a single bobbin, you can see I have taken single bobbin. Okay, if I have to draw more or little bit realistically, I can draw in this manner. Okay, so this is called the channel bracket, this is called the here, this is called the mounting foot. Here we have the lamination and here we have the coil, and this is the bobbin. So this is a single bobbin here. Okay, and if I am going to have a two bobbin, what is basically kind of two bobbin here, this is the two bobbin structure. Here we have a coil 1 and here we have a coil 2, and here the mounting bracket is not like this way, it is basically little bit of curve here, and that is basically known as tape C core. This is not a blind core, so tape C core, and then we are having a mounting bracket. Okay, and the bobbin is, this is not a bobbin, this is a coil here. Okay, the bobbin is above this coil. Okay, we can, okay, let me just draw a tape C core. I can simply draw the tape C core in this here. Here we have a curve here, this is the tape C core here. Okay, and this is a bobbin here. Okay, now I have talked on the toroidal also. Again if I am going to take a toroidal, it means we have a circle here, and we have a this thing here, we can do it, and then we have an outside here. So this is basically an effective window area, and this is basically a core. Okay, so this is so we have seen that in the transformer construction with the single bobbin, dual bobbin or a two bobbin, all these are basically defined quite differently, and we are only getting values basically very minor, like 0.75 or 785 or 687 or whatever values we are going to get it. Okay, so now let's come to the last factor of the window utilization, that's an insulation factor. So the insulation factors, it defines how much of the usable window space is actually being used by the insulation. Okay, so here in the insulation S4 factor, we are talking of an insulation, In an S3 we have talked upon the effective window, and in the S1 I have talked on the wire insulation. Okay, and in the second I have talked on the usable window area. Wire insulation basically is what? It was conductor area or the wire area. So let's take on the insulation factor. The insulation factor, it's going to define how much of the window space is actually being used by the insulation. Okay, now we can have a transformer which can have a multiple secondaries. We can see that we have an output 1, output 2, output 3 or an output 4. So when we are having a transformer with a multiple secondaries, so we can either use a higher or significant amount of insulation. So this as guidelines that if we are going to use the multiple secondaries, then this S4 should be reduced by 5 to 10%. Okay, this should be reduced to 5 to 10% for each additional secondary winding. Okay, because the added space is going to be occupied by the insulation, because partly the if we are having a multiple secondaries, the added space would be occupied by insulation, and the next would be by the space factor. Okay, so close this video.